I'd like to begin this talk with a list of dates from the history of geometry, some of which may be familiar to you, others less familiar or totally unknown. The list includes Euclid, Descartes, Euler, all of whom I'm sure you've heard of, but you may be less familiar with people like Theaetetus, Möbius, and above all, Schläfli. So let me try to explain how they fit into the subject of this talk. Theaetetus was a contemporary and friend of Plato, and together with Eudoxus was one of the outstanding mathematicians of the 4th century BC. His contributions to mathematics form the substance of books 10 and book 13 of Euclid's Elements of Geometry, which is referred to next on the list. Euclid, of course, wrote not just about geometry, but about virtually all the mathematics that was known at that time, and his famous textbook is really a compendium of mathematical knowledge up to the date 300 BC or thereabouts. I've put Descartes' name on the list because he introduced into geometry a revolutionary new method which enables us to go into higher dimensions in a very simple way from a technical point of view. Although at the time that Descartes was writing, of course, higher dimensional geometry had not been conceived of. Euler's name appears on this list, not only as one of the great mathematicians of the 18th century and perhaps of all time, but also because he contributed a major advance in the theory of polyhedra by noticing a relationship between the numbers of vertices, edges, and faces of any convex polyhedron, which I'll try to explain at an appropriate point in this talk. Möbius is mentioned here because he was perhaps the first person to look seriously at the possibility of higher dimensional geometry. And in 1827, as indicated here, he suggested that four-dimensional geometry would be a useful thing to explore for reasons that I will explain very shortly. Probably the least familiar name on this list is that of Schläfli. Ludwig Schläfli did the work for which he is now remembered right in the middle of the 19th century, and he achieved something that was quite remarkable for the time. He defined a concept of regularity for convex polytopes in space of any dimension, generalizing the classical notion of regular polygon and regular polyhedron, and he also achieved a complete classification of these objects, which I'll talk about at an appropriate point in the talk. Unfortunately, his work was unknown at the time and was repeated by several mathematicians towards the end of the century, but now he is beginning to get the credit that he deserves. Before we embark on an exploration of higher dimensional geometry and some of the interesting objects that we find there, I will have to indulge in a brief discussion of elementary Euclidean geometry. And so for the next few minutes, I'm going to attempt to give a crash course in Euclidean geometry of n dimensions in perhaps only 2 or 3 slides. Let me first define what I mean by Euclidean space using Descartes' ideas of specifying the dimension of a space in terms of coordinates. So Euclidean n-dimensional space is denoted in this talk by En, and n can be any number 1, 2, 3, 4, 5, 6, and so on. So E1 is a line, E2 is a plane, and E3 is Euclid's model of physical space based on experience of touch and sight and sound. E4 is Euclidean 4 space, and one of the commonest misconceptions about Euclidean 4 space is that it's the space in which the theory of special relativity is discussed. Now, there's a sense in which that's true and a sense in which that's false, and I'll try just very briefly to explain what these are. As sets and as topological spaces and as linear spaces, Euclidean space and Minkowski space, that is the four-dimensional space-time in which special relativity is discussed, are the same objects. Where they differ is in their metric structure, and while I don't have time to explain the metric structure of Minkowski space, I will try to explain what the metric structure of Euclidean space is. Well, let's look at Descartes' approach to geometry. He invented what we now call coordinate geometry or analytic geometry, and its main idea is to convert geometry into algebra. So let me just remind you of what that entails with a very simple example. In the plane, we might consider a circle with center capital A and radius capital R, say. Then that circle is specified completely by an algebraic equation. X minus a all squared plus y minus b all squared is equal to capital R squared, where in this symbolism, xy is a variable point on the circle, and capital A is the point with coordinates in Cartesian sense, little a and little b. So a point of the plane E2 is just an ordered pair, x, y, of real numbers, which are called the coordinates of the point. And these measure the perpendicular distances of the point from a pair of perpendicular lines called the coordinate axes, with proper account being taken of directions, which is expressed algebraically in terms of the signs of the coordinates themselves. The coordinate axes, of course, cross at the origin O. Carrying on that idea into higher dimensions, a point of Euclidean 3 space is a triple x, y, z of real numbers, and in the same spirit, a point of E4 is a quadruple x, y, z, w, or, since the numbers are getting rather extensive now, x1, x2, x3, x4, all of these coordinates being real numbers. And then it's a very short step to see that a point in En should be an n-tuple x1 up to xn of real numbers. And the picture here simply reminds you how x, y, and z are calculated for a point in Euclidean 3 space. X, y, and z are marked by these red lines and measure distances from the appropriate planes. By having defined Euclidean space as a set, we now impose on it a metric structure. And in order to do that, we have to specify what we mean by distance, and we have to specify what we mean by angle, these being the main ingredients of Euclidean geometry. It turns out that both of these ideas can be derived from a notion that is familiar in linear algebra, the inner product operation. What I've done here is simply write down the general definition of inner product, the acute brackets xy, capital XY of 2 points x and y in Euclidean n space is defined by the formula x1, y1 plus up to xn, yn. The meaning of that is easily understood once we interpret our ideas of distance and angle in terms of it. So the distance from capital X, for example, to the origin is the square root of the inner product of x with itself, and the distance from any point x to any point y is the square root of the inner product of x minus y with itself. Well, that may seem mysterious until you relate it to a very famous theorem of antiquity, namely Pythagoras' theorem, and a close study of the formula will reveal that it does no more than restate Pythagoras' theorem in algebraic terms. Likewise, our measurement of angles is defined in terms of the inner product and is given by the formula at the bottom of this slide, which is simply a general form of a familiar theorem in plane geometry, the cosine formula for triangles. We won't make much use of these formulae later, but at least I hope it will give you some confidence in the feeling that the metric structure of Euclidean n-space is well defined. Now let's go back to the list of dates and recall that Mobius was mentioned as the first person to consider the possibility of four-dimensional geometry, and I'd like to just mention the idea that led him to that consideration. Here's a picture of the outlines of two hands, a right hand and a left hand, and I've cheated here by tracing out my right hand and then reflecting it in a tracing paper so that the two hands look exactly like one another, differing only in orientation. Hands, of course, are three-dimensional solid objects, but let's imagine for a moment that they are completely flat, so that they're just subsets of the plane. Then, if the hands are confined to 2 dimensions, it's impossible to transform the red right-hand picture into the blue left-hand picture simply by sliding one across the plane. In order to transform one into the other, it's necessary to go into 3 dimensions. And an easy way to do that is simply to rotate one picture in 3 dimensions and lay it down again in the original 2-dimensional plane with the orientation reversed. Well, that's a familiar idea, I think, but in the 18th century and the early 19th century, it was thought that the analogous problem in 3 dimensions had no solution. We can get some feeling for this by looking at the next picture, which is a picture of 2 screws, one a left-handed thread and one with a right-hand thread. And again, these are mirror images, but this time the mirror is a 2-dimensional mirror, and I think it's quite clear intuitively that it's impossible to move one of these about in 3 dimensions to superimpose it on the other. Orientation problems intervene, and so in 3 dimensions there is an essential difference between left-handedness and right-handedness. What Mobius suggested was that if we could move in 4 dimensions, then we could construct an analog of the procedure that I described for 2 dimensions, and simply take the right-hand thread and rotate it in 4 dimensions, superimposing it then on the left-hand thread. So from a 4-dimensional point of view, the difference between left-handedness and right-handedness in the 3-dimensional sense disappears. Once this idea had been explored, the gateway was opened to developing n-dimensional geometry seriously, and many mathematicians at that time began to make very important contributions. Well, what I'm going to do is to try to indicate how 4-dimensional objects can be visualized in a perfectly acceptable way by looking at them as analogs of corresponding objects in the plane and in 3 dimensions. So for the next few minutes, I'd like to examine some interesting objects in the plane and in 3 dimensions. Let me begin with some very familiar objects indeed. On the left, we see a sequence of regular plane polygons, the equilateral triangle, the square, the regular pentagon, the hexagon, and so on. And I've denoted these by P3, P4, etc., the suffix indicating the number of corners, and that, of course, is the same as the number of edges in each case. I've also indicated by means of an arrow that if we allow the n of Pn to increase indefinitely to tend to infinity, then the limit of this sequence in an intuitive sense is a circular disk, which I've put at the right-hand side of the picture. Now, you may expect that the title of this slide should be the regular polygons, or the regular convex plane polygons, but instead we have this less familiar term, the perfect two solids, and I'd like to try to use this term not only in the plane but in the three space and higher dimensions to describe a type of convex body that in some sense is a modern analog of the classical idea of regularity. Perfection in this sense refers to a kind of rigidity, and if you look at each of these objects, including the circular two-disk, you will see that it's impossible to deform any one of these objects in the sense that its shape is changed. It's possible to change its size and its position in space, but if you change the shape of any of these objects, no matter how slightly, then you modify its symmetry behavior. That's true of the circular disk. It's also true of these regular polygons. And it's not a very difficult task to show that these are the only convex bodies in the plane with this property. So indicated here is an infinite sequence of perfect polygons and their limit, the perfect solid, two-solid, called the circular two-disk. These are the only perfect two solids. With such an easy solution to that question, we might ask, what are the analogues of these objects in three dimensions? Well, there is one very famous family called the Platonic solids, which are the natural candidates for this title. These objects are called the Platonic solids not because Plato discovered them, but because Plato made very interesting use of them in his dialogue Timaeus. And the first name on the list at the beginning of this talk, Theaetetus, is the person who made the first very important contribution to the theory of these objects. He showed that they formed a unique family in the sense that the five objects shown here share a very simple property that is enjoyed by no other objects in three dimensions. The property is that they are convex polyhedra with faces that are regular polygons, all of one type, and the same number of such faces meet at every corner. And indeed, in Book 13 of Euclid's Elements, you can find what is believed by scholars to be Theaetetus' argument showing that these objects are unique in this respect. So let me very quickly try to give the modern equivalent of that argument. Let's begin with a very familiar theorem that in any triangle the sum of the internal angles is pi, that is 180 degrees. If you look at the first two triangles, you will see silent proofs of this theorem. I don't think they need any further explanation. They simply make use of very elementary theorems of classical geometry. This theorem can then be extended to an m-sided convex plane polygon, and it states that the sum of the internal angles is m minus 2 times pi, where again pi is 180 degrees. And the little bit of algebra that I've appended at the bottom of this transparency indicates how that proof goes. We simply add up the formulae for the various triangles into which a polygon can be divided by joining the vertices to a point inside, for example, the centroid. Now, this idea can be applied to the case of a regular polygon, because if all the internal angles are equal, then each must be equal to m minus 2 pi divided by m. For example, if m is equal to 3, then each angle is pi over 3, that is 60 degrees. Now, a convex polyhedron is said to be regular if all its faces are regular polygons and the same number meet at each corner. So we can specify such a polyhedron by a pair of numbers, p, the number of edges in each face, and q, the number of faces at each vertex. So we can talk about a regular polyhedron of type PQ. For example, the 5 regular solids are of types 3, 3, 3, 4, 4, 3, 3, 5, and 5, 3, respectively. And that's very easy to check. Now the argument goes as follows. Since each polyhedron is convex, the sum of the angles of the faces at each vertex must be less than 2 pi because of convexity. If the polyhedron, for example, were flat at a vertex, then the sum would be equal to 2 pi. Since there are q of these at each vertex, and each angle is p minus 2 over p times pi, it follows that q times p minus 2 over p times pi is less than 2 pi. And a little elementary algebra, which you might enjoy doing, shows that this is equivalent to the inequality 1 over p plus 1 over q is greater than a half. And it's only the work of a few minutes to check that the only solutions in integers for p and q with both at least 3 are the ones that we've indicated. So that's a restatement of that classical argument. So there are only 5 Platonic solids, but if we adapt the notion of perfection that I tried to explain for 2-dimensional convex bodies to apply to 3 dimensions, then we have a notion of a perfect 3 solid, and it's easy to see that each of the Platonic solids is a perfect 3 solid. But it turns out that there are other perfect 3 solids. The spherical ball, for example, is perfect in this sense, and so are 4 other convex polyhedra, the cuboctahedron, the icosydodecahedron, the rhombic dodecahedron, and the triacontahedron. These polyhedra share with the Platonic solids the property that their symmetry group, if you know what that means, acts transitively on the edges of the polyhedron. And these are the only convex polyhedra with that property. Behind me, you will see a model of a triacontahedron. And if you wish to make a model of this kind, it's very easy, provided you have the patience. You have to make 30 rhombuses, that's 30 diamond-shaped polygons, quadrilaterals, in which the length of the long diagonal bears the ratio tau to the length of the short diagonal, where tau is the golden number 1/2 root 5 plus 1. Well, this may be an appropriate point at which to mention Euler's polyhedral formula. Many people believe that Descartes proved this 100 years or more before Euler, but the weight of evidence seems to suggest that although Descartes was very close to this in the sense that he proved 2 relationships which together imply this theorem of Euler, he did not in fact notice the theorem itself. The theorem says that in modern language, any convex polyhedron with V vertices, E edges, and F faces has the property that V minus E plus F is equal to 2. And I've appended the corresponding calculations in the case of the 5 regular solids, but the force of the theorem is that it applies to any convex polyhedron. Well, now I'd like to start building up a menagerie of objects which make sense in every dimension and whose geometry we can understand easily in dimensions 1, 2, and 3, and whose geometry in 4 dimensions I hope to make accessible to you. The first sets of pictures of these 4-dimensional objects may not mean very much, but I'd like to suggest techniques as the lecture develops which may help. First of all, let's look at the n-dimensional simplex, which I denote by delta n. In 1 dimensions, a 1 simplex delta 1 is simply a line interval. In 2 dimensions, it's just an equilateral triangle. In 3 dimensions, it's a 3-dimensional simplex or tetrahedron. And in 4 dimensions, it is something that we have to try very hard to imagine. And what I've drawn here is a projection of the vertices and edges of such a 4 simplex onto or into the Euclidean plane. It may help you in exploring the geometry of this object if we specify a very simple way to describe such a simplex. If we take the vectors e1 up to en plus 1 in n plus 1 space to be the natural basis vectors, so that e1 has coordinates 1, 0, 0, 0, and so on, and en plus 1 has coordinates 0, 0, 0, ending with 1, then an n simplex is most simply represented in n plus 1 space as a subset of the hyperplane for which the sum of the coordinates is 1, with the vertices e1 up to en plus 1. So this simplex is the intersection of the positive orthant of Euclidean n plus 1 space with this hyperplane. The next set of objects that I'd like to mention I call the co-cubes, although they're often known as cross-polytopes. Again, in 1 dimension, the 1 co-cube is the same object as a 1 simplex. It's just a compact line interval. And I've specified its 2 endpoints. They are the points e1 and minus e1, that is, the real numbers 1 and minus 1. In 2 dimensions, a 2 co-cube diamond 2 is just a square, but naturally it seems it should be poised on its corners in the way that I've indicated here, rather than resting on its edge. And that's because the simplest way to specify its vertices is by means of the vectors plus or minus e1 and plus or minus e2, where here in the plane e1 is the point 1, 0, and e2 is the point 0, 1. Well, likewise, a 3 co-cube is the same thing as a regular octahedron. And I've indicated on the right in red a vertical view of such an octahedron, a fairly familiar object, with the top and bottom triangles shaded in to suggest the 3-dimensionality of that picture. And at the bottom in purple, there is a picture of a projection into the plane of a 4 co-cube diamond 4 with all its vertices indicated here, plus or minus e1 up to plus or minus e4. And if it's difficult to see how the faces of this object appear in the picture, let me indicate how these may be visualized. Here's a picture of an octahedron, which is a typical face of this object, a 3-dimensional face of a 4-dimensional object, and you can trace where that sits in this picture. There's many other positions, of course, for such an object. Well, I'm not trying to suggest that this will give you any great insights into 4-dimensional geometry at this stage, but I hope as these pictures begin to develop that some kind of intuitive understanding of high-dimensional geometry may begin to emerge. So let me look next at a very nice family of objects that occur in every dimension, the cubes. A 1-dimensional cube, rather monotonously, is the same as a 1-dimensional co-cube and is the same as a 1-dimensional simplex. It's just a closed line interval. And again, in the plane, a square is the same thing as a 2-dimensional cube, and that, of course, was the same as a 2-dimensional co-cube. But in 3 dimensions, these objects begin to present different appearances. A three-dimensional cube is the familiar cube, square 3, and I've indicated how to specify the corners or vertices of such a cube simply by indicating the signs, which should be plus or minus 1, of each of the coordinates of these points. So, for example, the point plus plus minus is the point 1, 1, minus 1 in 3 dimensions. And below that is a picture of a projection of a 4-dimensional cube into the plane, and the various sequences of pluses and minuses indicate the coordinates of a nice choice for the vertices. So, for example, minus plus plus minus is the vertex with coordinates minus 1, 1, 1, minus 1 in 4 dimensions. In general, an n-dimensional cube has vertices plus or minus 1, and so on, up to plus or minus 1. So the point 1, 1, 1, 1, 1 n times is an example of a vertex of square n. Now, the last family of objects that I want to present as aids for visualization in n dimension is the family of spheres. A zero-dimensional sphere is just a pair of points. A one-dimensional sphere is a familiar object, namely a circle. A two-dimensional sphere is what we commonly understand by the term sphere, although I'd like to emphasize that we're talking about the surface of a ball rather than the ball itself. So, for example, to say that the Earth is a sphere means that the surface of the Earth is more or less a sphere. In a Cartesian sense, the specification of a sphere in n dimensions, now notice that that should be Sn minus 1 here. Sn minus 1 is the set of points with coordinates x1 up to xn in n space for which the sum of the squares of the coordinates is equal to 1. So it's a sphere with center of the origin and radius 1. Well, these are objects that each of which forms a series occurring in every dimension from 1 onwards. But now let's look at 4 dimensions and beyond and ask ourselves the question, what are the analogues of, say, the Platonic solids or the regular polygons in higher dimensions? Well, that's a question that Schläfli asked more than 100 years ago, and he was able to answer it. He gave 2 answers, 1, the answer for 4 dimensions, and 2, the answer for n dimensions. And there's a remarkable difference between these two. In 4 dimensions, there are up to changes of position and size, that is, up to similarity, exactly 6 regular convex 4 polytopes, that is, analogues of the Platonic solids. And these are the regular 4 simplex, the regular 4 cocube, the regular 4 cube, and 3 rather strange objects known as the 24 cell, the 120 cell, and the 600 cell. And unfortunately, there's no time for me to explain how these are defined in any detail, but I will try to pick one of them, the 24 cell, and give you some idea of what it looks like. Schläfli also showed that in higher dimensions, such maverick objects do not occur. There are only the simplices, the cocubes, and the cubes as the regular objects in higher dimensions. One of the things I'm trying to do with my colleagues is to determine the perfect solids in 4 dimensions and higher dimensions. And we have a very firm grip on this problem in the sense that we are very close to solving it. We have a set of candidates which we believe is a complete set, but we're not quite in a position to prove that yet. So now let's go on to the real purpose of this lecture, not only to define objects in higher dimensions, but to try to see them in some sense. So let's begin with a four-dimensional cube, and I'll start with a very easy way to make a two-dimensional cube or three-dimensional cube and show you an analogous construction for a four-dimensional cube. So on the left here we have the kind of picture that you might draw if you wanted to make a 3-cube out of, say, a sheet of cardboard. You might draw 6 squares joined together as indicated, and then cut along the outline. The colouring is intended to indicate which edges you glue to which. So, for example, the edge DC is glued to the edge DC at the bottom here. And most children derive great pleasure from making models of this kind, and it's a pleasure that continues into adulthood for many of us. On the right, there's a picture of the corresponding construction for a four-dimensional cube, where this time, instead of just having 6 squares, you have 8 three-dimensional cubes as the component faces, and you can colour these in the way corresponding to the easy case, indicating which faces should be glued together. So, for example, the 2 red faces should be glued together, and then the 2 green faces should be glued together, and so on. Physically, you find this is not possible to do completely in 3 dimensions, but you can get very close to it. And using an idea due to Schlegel, you can get something approaching a picture of a four-dimensional cube. So here on the left is a Schlegel diagram of a three-dimensional cube, and on the right a Schlegel diagram of a four-dimensional cube. How are these constructed? Well, to construct a Schlegel diagram of an ordinary 3-cube, you simply place your eye very close to one of the flat faces and then look at the cube and see what you see. So, for example, this picture could be imagined to be a view of a transparent cube when you've placed your eye very close to the top face. Alternatively, it's a view of a cube where you think of the cube as a box with no lid, and you're looking down into the box. And correspondingly, on the right, you can describe another simple construction which gives you this picture of a four-dimensional cube. And if you look closely at it, you can see each of the cubical faces, some of them certainly distorted, so 2 of them appear as cubes, the inner and the outer one. The other 6 cubical faces are distorted by the perspective of the picture. Well, that may encourage us to try to explore higher dimensional space in terms of splitting the space perhaps into factors. And here's an idea that we might pursue. Euclidean n space can be thought of as Euclidean k-dimensional space times Euclidean n minus k-dimensional space. For example, Euclidean 3 space can be thought of as a line, that's E1, times a plane, E2, with a line, say, as the z-axis, and the plane as the xy plane. So any Euclidean space can be split up as a product of orthogonal factors in this way. And we find that that's a very helpful way to think of, for example, an n-dimensional sphere. Here's a picture on the left of an ordinary 2-dimensional sphere in 3 space, and what I've indicated here are the intersection of Euclidean 1 space, the z-axis, with the surface of the sphere, and as you know, that gives us 2 points, the north and south poles. That's a zero sphere. The xy plane, the horizontal plane, intersects the 2 sphere in a circle, and we commonly call that the equator. The two green curves parallel to the equator above and below it you can think of as the tropics, and these divide the sphere into three regions: the two polar caps and the equatorial belt. And so we can express S2 as a product of a zero sphere, that's a pair of points, with a disk, the polar cap in each case. So S0 cross D2 is a pair of disks, the two polar caps, joined up to a cylinder which is a one disk, that is just an interval, and a circle, S1, a one sphere. Now, from the same point of view, we can split 4 space into a line and a three-dimensional space, but we could also split it into the product of a plane and another plane. The first plane generated by the x1 and x2 coordinates, and the second plane generated by x3 and x4. Now, from that point of view, the two planes that we're considering as the factors of E4 will each intersect the surface of the three-dimensional sphere S3 in a circle this time, not in a pair of points and a circle, but in each case a circle. So we have two circles that don't meet one another as the equivalents of the equator and the poles. And instead of the two tropics, the two green curves, we find what we've got a torus, and I've indicated here a picture of what that torus might look like. Well, the equatorial belt then is replaced by the product of a circle with a disk, and so are the polar caps. The polar caps become a single connected piece of the sphere, and they also are in the form of a disk times a circle. But this time, the two factors are interchanged. So S3 is the union of a circle times a two-disk and a two-disk times a circle. And the factors are written in this reversed order deliberately, because when you look at the boundary of each, you'll find that to match them together, the two factors must be interchanged in this way. And the picture on the right is intended to help you visualize the three-dimensional surface of S3 that you get if you simply notice that the surface of a three-dimensional sphere from which a single point has been removed can be spread out to cover the whole of Euclidean 3 space. So E3, from a topological point of view, is the same thing as a sphere, three-dimensional sphere, with 1 point removed. So here is a picture of a three-dimensional sphere identified with Euclidean space E3 with an extra point at infinity, if you like. And the two blue lines are the two equivalents of the equator and the poles, as I've suggested. So that's one way to picture a three-dimensional sphere as the union of two solid cylinders. Now, if we recall the Schlegel diagram for a four-dimensional cube, it's not very easy to see the 4 cube as the product of other objects. But a four-dimensional cube is in fact the product of two squares, and in the same sense we can construct objects in 4 dimensions which are the product of pairs of polygons. And here I've drawn a picture of a Schlegel diagram of the product of two polygons, P3 and P5, where you may remember P3 is an equilateral triangle and P5 is a regular pentagon. And there are two ways to look at this picture. One, that you have a circuit of pentagons, and the other you have a circle, a circuit of triangles, each one corresponding to some kind of prism. So in the middle here we have fairly visibly a triangular prism, below it another triangular prism, two further triangular prisms on top of that, and then enveloping them a fifth triangular prism. So we have a circuit of 5 triangular prisms. Equally, going round in a horizontal sense, you can pick out 3 pentagonal prisms which form the other way to look at this object. Well, time is running on, and I'd like to try to reach my destination, which is to suggest how you might try to visualize one of the 6 rather strange regular polyhedra, or polytopes, in 4 dimensions. And to that end, I'd like to begin by showing you one way to construct a rhombic dodecahedron. I don't know if these pictures will explain this very clearly, but it's a very easy idea to understand. On the left, we can start with a cube indicated in green, an ordinary 3-dimensional cube. And what we do is take the vertex, a new vertex, which is obtained by taking the center point of each face and pulling it out vertically or perpendicularly from each of the faces. Now, if you pull each vertex out the same distance, or each center out the same distance, and that distance is very small, then what you get is a new polyhedron with 4 times as many faces as the cube, but each of these faces is now an isosceles triangle. But suppose we continue to pull this vertex out, then there will come a point at which adjacent triangular faces abutting the same green edge of the cube will become coplanar. At that point, the number of faces drops from 4 times 6, that's 24, to half that number, 12, and we get an object whose faces are diamond-shaped and which has 12 faces. So it's a kind of dodecahedron, and since each of the faces is a diamond, that is a rhombus, we call it the rhombic dodecahedron. And on the right is a picture of this construction when it's reached that stage. Now, to construct the 24 cell, one way to proceed is to repeat this procedure, but this time, instead of starting with a 3-dimensional cube, we start with a 4-dimensional cube. More generally, you could do this with an n-dimensional cube, and the result is an object like this. On the left, I've drawn an ordinary 3-dimensional cube, but suggested that what I'm looking at is an n-dimensional cube, and I've written down the coordinates accordingly. Epsilon is the distance through which we move the center of each face vertically from the face, and what I've done here is to calculate in terms of our simple Pythagorean formula the distance from the raised vertex to a typical corner of the corresponding face, and we consider the relationship between that and the edge length of the cube itself, which is 2. Now, the point at which the 2 pyramids, or the 2, in the 3-dimensional case, the 2 isosceles triangles become coplanar, is the point at which epsilon is equal to 1. That's very easy to calculate. And it follows, therefore, that the distances that we're trying to make equal will be equal when the square root of n is equal to 2. That's a very elementary calculation here. Now, the square root of n is 2 if and only if n is equal to 4. And that's one way of reaching some kind of understanding of why there is a 24 cell in 4 dimensions, which turns out to be a regular polytope, but the corresponding objects in higher dimensions and indeed in lower dimensions turn out not to be regular. Well, on the right is a very complicated looking picture, which is a 2-dimensional projection from a suitable standpoint of the resulting 24 cell. It's called a 24 cell because it has 24 3-dimensional faces, each of which is a 3-dimensional octahedron, a regular octahedron or 3-dimensional co-cube in the sense that we've explained already. And in the spirit of the diagrams that I drew before, we can stare at this picture and try to see where the various octahedral faces lie. Here's a picture of a regular octahedron, and here is how it might fit on to this picture so that it can help us detect the various 3-dimensional faces of this 4-dimensional object. On the right, I've listed simply the numbers of the various faces. There are 24 vertices, 96 one-dimensional edges, 96 equilateral triangular 2-dimensional faces, and 24 regular octahedral 3 faces from which the name of the object is derived. It doesn't take very much mathematical ability to realize that 24 minus 96 plus 96 minus 24 is 0, and that might give a hint of how Euler's polyhedral formula might be extended to 4 dimensions. We simply take the alternating sum of the numbers of faces of each dimension, and we find that that alternating sum is 0 in every case. Schläfli proved this, and he also showed that the corresponding general formula for n dimensions actually works also. That is, the alternating sum of the numbers of 0 faces, 1 faces, 2 faces, and so on turns out to be 1 minus 1 to the n. So that in odd dimensions it gives 2, in even dimensions it gives 0. Well, we've almost reached the end of this story, but perhaps I should just mention that 2 of the objects that we've been studying today can be thought of as 3-dimensional projections of higher dimensional objects that we've also been discussing, namely higher dimensional cubes. The rhombic dodecahedron, for example, can be represented as the vertical or orthogonal projection into 3 dimensions of a 4-dimensional cube, and the triacontohedron behind me can be presented as the projection into 3 dimensions from a suitable standpoint of a 6-dimensional cube.